Hey AP Calculus students, this is the video for Friday, January 18th, and this is going to get you started in the first part of Chapter 4 in your textbook. So what we're going to cover today involves a topic known as antiderivatives and then also what's called indefinite integration. So go ahead and take a look first up on your slide, and you have these in note packet form at the front of the room. Or if you just want to work off of your own notes, if it feels too small to work in the notes packet, that's fine too. So what we want to do today is to watch this video to get you through the basics of the content that's covered in section 4.1. Then you want to start on tonight's homework, which is going to be a lot of straightforward practice problems where you're just applying the different algorithms for evaluating these problems. And then last up, I just want to make note that Tuesday, so when we all come back together, we'll have a practice day in section 4.1, and you will also at that time have a chance to reattempt the bonus from yesterday's quiz. So if you ran out of time on that one, you'll have a chance to look at it again. So what we want to think about today, you guys, is what is an antiderivative, which in calculus is also called an integral. So today we're getting started on what is our third of three major calculus topics. So you've completed everything that you need to know for calculus involving limits and all of our major topics in differentiation. So that means we're moving on to our final big topic, which is called integration. So in these two bullet points here, what you have is the two essential questions behind derivatives and then the reversal process or integration. So first up, it says derivative work asks you to consider if you see a function, what is its derivative? So what is its slope? Now we're just reorienting ourselves in our content, and instead of coming across a function and wanting to find out its slope, we're asking what other function is this function the slope of? So we're just working backwards. So here, if you see a function, which function's derivative is it? Now what it mentions here is that derivatives and integrals have two key real-world purposes. So when it comes to the use of derivatives, derivatives are focused on identifying rates of change, so how something changes over time. When it comes to antiderivatives, which is another word for integration or the reversal process of taking a derivative, it means something slightly different in context. So we will talk at great lengths about what it means to integrate a real-world function, so what it is that you're solving for when you do that. But for right now, we're going to focus on the basics. So just like we learned our original derivative rules of constant rules and power rules and our basic trig functions, all that we're emphasizing today is how we can go backwards in that type of operation. Now, when it comes to working with antiderivatives, we refer to antiderivative work as integration or the use of integrals. And this symbol, this long-looking S that we use, is called an integral sign. So that sign says, instead of taking this function's derivative, like d dx or f prime asks you to do, it says go backwards. Find the function whose derivative would be the function that you're provided. So in this setup, you will always have a function, and you have what's called a dx or a dy, depending on what you're trying to integrate with respect to. So if your variable of interest is x, you will have a dx. If your variable of interest is y, you'll have a dy. That's the same thing as when you have d by dx, that means take the derivative with respect to x. In this case, the dx component just means take the integral with respect to x. So we want to go ahead and dive right in to some work here, because just like with derivatives, the more you get going with this process, the more rote and intuitive it will become. So here it says, find the equation, general equation, to the differential equation y prime is equal to 7. So a differential equation means that you have an equation that involves derivatives. So it can either have first derivatives or second derivatives, or you can put different order derivatives in combination with one another. If you continue on in college level math, you'll likely take an entire course just on how you come up with functions that are involved in differential equations. We will get into some very basic and clear types of differential equations, beginning with this one that we have here. So this says, there is a function y who, if you take its derivative, you will end up with 7. So this is going to be really nice and easy to solve. All we need to do is say, okay, we know that y prime, kind of overdid that one, y prime is equal to 7. So in order to undo that derivative piece, we go ahead and just use this long S sign, which means take that function's integral or reverse the derivative process. So anytime you have a constant and you work backwards with integration, you're going to end up with a linear function. So that's what this rule says. If you just have a number that's a constant, working backwards, you'll end up with that number times x. So when we take the integral of a derivative, the derivative sign goes away, and we're left with y is equal to 7x. Now, when it comes to working with integration, we always include a plus c for general solutions. The reason that they're called general solutions is that I could have any constant. I could say plus 2 or plus 10 or plus 25. And no matter what I do when I take the derivative, those constants will always go to 0, but the derivative value will still match up. So we include that plus c to represent the constant of integration. Now the nice thing is, you can always confirm that you integrated or reversed the derivative process correctly by taking the function's derivative. So if I come across the function y equals 7x plus any constant, we could, for example, have something like y equals 7x plus 6. When we take that function's derivative, y prime, we just end up back at 7, which is where we started out with when we began. So that's all that integration is, working backwards. So you can always move forward and make sure that you did your steps correctly. Now, that was going from a constant to a linear equation. We want to be able to work with any function that has an exponent. So we really want to be able to reverse our power rule. Now, when it comes to your derivative process, let's say you have something like 3x to the third. What you do here is that you bring your 3 out in front and multiply together. So this derivative would be 9x squared. So working backwards for these kinds of functions, what we're going to do is take a look at whatever function we start out with. And if we want to take its antiderivative or integral, we're going to have that funky symbol. And what we're going to do here is just take a look at whatever value we have in the exponent, and we're going to add 1 to it. So right now there's a 5 in my exponent, so if I add 1, I'm going to end up with 6. And then whatever number I end up with when I added 1, I'm also going to divide my function by that same number. And then I add my constant of integration to say, hey, any constant could be hanging out on the end, and I would still end up with the same derivative if I go backwards. So this is my general antiderivative. And you could write that as 1/6 x to the 6th, or just as x to the 6th over 6. Now, if I want to work backwards, if this is my function y, when I find y prime, I would move that 6 out in front. I'd end up with 6 times 1/6, and then the exponent would become 5. The constant's derivative would just go to 0. So this would become x to the 5th, which is where we started out with. So we're taking the exponent, adding 1, and then also dividing by that same number. So let's try a few more. All of these values have constants along with them, and that's just fine. So our goal here is going to be to find the derivative, so to reverse the integration process. And all I have to do with constants is to bring them along. So if I want to go ahead and integrate this function with respect to x, I can simply rewrite it as 9 times the integral of x cubed dx. So I simply pull the constant out in front before integrating. From there, I follow the process where I add 1 to my exponent. So that 3 is going to become a 4. And then I divide by 4 as well. And I add the constant to demonstrate that any constant could be added and would end up with the same derivative. Again, if I were to check f prime of x for my new function, what I would find is the 4 comes out in front. Those would cancel. I would subtract 1 from the exponent, so I would end up with 9x cubed. Let's do the next one. Here we have 7x to the 4th. So if I take this integral, 7x to the 4th with respect to x, I can pull the 7 out in front, and I've got x to the 4th dx here. The 7 comes along with my x. It increments up to 5, and we also divide by 5. And then I just add a constant. Now, if any of these fractions can be simplified, I want to go ahead and do that. So far, 9/4 and 7/5 can't be simplified, so I'm stuck there. Then we've got another one, but this time we have some decimals going on. That's okay, the process works exactly the same with decimals. But I'm going to go ahead and move this example over to the right just so we have a little bit more room. If you have multiple terms added together in an integral, the process flows using the same kind of techniques we use with derivatives. So you can think of it as you're handling them each individually by individual function piece, but then they can just all be pushed together when you're adding or subtracting. So here I'm going to say the integral of 0.75 x squared plus 0.5x plus 10, and then I have a dx over here. So when I integrate this term, the constant just comes along out front. So I end up with 0.75. The square is going to become a 3, and I'm going to divide by 3. Then if I look at this term, there's really a 1 above that x. So I'm going to end up with 0.5x squared because I go up by 1, and then I'm going to divide that by 2. And then this 10 is a constant, which we just looked at on the previous couple of slides. So that's going to become 10x, and then I've got a plus c over here on the end. So that's my antiderivative, or my integral of the expression that we have there. But looking at this one, we probably would want to go ahead and simplify from there. So this would become 0.25 x cubed plus 0.25 x squared plus 10x plus c. Now you don't want to forget the plus c when you report these answers, otherwise it's not considered fully correct. So that's true on AP exam work as well, that you'll see that constant of integration added along anytime you take a general form of an antiderivative or integral. Last one is just a fraction, single term fraction down here. So we have f of x equals 1/3 x to the 10th. So if I integrate this with respect to x, we could pull the 1/3 out in front. And then we've got x to the 10th dx here. So I'm going to increment up my 10 to 11, and I divide that by 11 as well. So if I want to write this out, I'm just going to simplify this guy to 1/33 x to the 11th, plus I'm bringing along the constant there. So that's our basic operation when it comes to integrals and antiderivatives. Now we've got a couple here on the next slide that aren't quite as lovely of polynomial structures as the ones that were previously presented. So here we're going to have some negative exponents to deal with and some fractional exponents. But we don't need to worry, because just like with regular derivatives, if we rewrite the expression first and then apply our general rules, it's the exact same as our power rule work. So if you take a look at your example 1, you have 2 times the cubic root of x. So I'm going to go ahead and rewrite this as 2 times x to the 1/3. And then I can integrate that with respect to x. I'm going to demonstrate that I'm pulling the 2 out in front, and I've got 1/3 here. So then when I go to integrate, I'm still adding 1, but I'm adding 1 to 1/3, which you can think of as saying 1/3 plus 3/3, which is equal to 4/3. So this is going to become 2x to the 4/3, and then I still need to divide by 4/3. But dividing by 4/3 is the same thing as multiplying by 3/4. So I'm going to have 2 times 3 over 4, x to the 4/3. 2 times 3 is going to become 6. 6 over 4 is going to reduce to 3/2. So I'll have 3/2 x to the 4/3. And then just like all the other examples, I want to include that plus c at the end. Then let's take a look at the negative exponent one that we have over here. We have 7x to the 5th in the bottom part, so in our denominator. So we can rewrite this expression as the integral for 7x to the negative 5th with respect to x. I'm going to pull the 7 out in front. I've got x to the negative 5th left inside. Same thing as before, I'm going to add 1 to that value and then also divide by that. So I'll have 7x to the negative 4 divided by negative 4, and then plus a constant, which I do want to go ahead and rewrite. So I'm going to say negative 7 over 4 x to the 4th plus c, and that's going to be my final answer there. So go ahead and check online for the second video, and that will get you through example 3 on this slide and then the remaining content for today's lesson.